All right. So as you were finishing writing that, going back in the past, yes, 2 days in the past, right? Okay. So two things. AP readiness is Saturday. Okay, so tomorrow, about 8:45. Make sure you're logging in. All right. Let's get. There's only 2 of those left. All right. Go to the one that says rates. I'm going to guess that's where Lundstrom is tomorrow. And his lesson, I know some of you have seen it, but it's a really good refresher on rates because you know those are going to be all over your AP test. Those are on both exams. Okay. So you want to make sure you've gone in and refreshed yourself on that. If you guys do that, then there's less we have to do. We can get into some of the stuff that's more newer for your test this year when we get closer to tests. The other one is next Saturday, so the 13th, from 10 to 12. We're going to be doing a Hemet Unified March multiple choice madness. So it's been a while since we just looked at just multiple choice questions and techniques on those. So we're going to do those next Saturday. So come in and come see Mr. Kiza and Mrs. DeWitt and myself, and maybe they'll teach their part a little bit differently than I teach my part, or that I teach, and maybe you'll pick something else up. It will be AB material, but again, you need the review. Okay, so the more you can come to doing my BC students, I typically have you kind of do double duty. So we get the AB stuff with the AB kids, and we add our little layer onto it. Okay, of little tiny stuff that's BC. Okay. You have to unfortunately bridge both, but you're strong calculus students. You can do it. Okay. It just takes us, we haven't seen it in a while. Let's review it. Okay. All right. So let's talk about power series. And it's not something to freak out that we don't know what this is. You guys have been working, we just started working with power series sort of earlier this week. We just called them Taylor and Maclaurin polynomials. Okay. Both of those are power series. And those are the 2 power series we typically see on the AP test. Okay. So our goal today is to show how an infinite polynomial function can be used as an exact expression for other elementary functions. For example, the function f of x equals e to the x can be represented exactly by this polynomial that's listed there. The way they got that polynomial was by doing a Maclaurin series. Okay, so when we create it and we turn it into a series officially, we call that a power series. Okay. There are some of these power series. I did tell you guys you guys' test is going to be pencil and paper, right? May 24 on campus. Okay, in some way, shape, or form. All right. So we're going to have to get back to we're going to have to memorize some stuff. Okay. There are a few of these series you're going to want to memorize. All right. So when these come up today, just know that there's a list of them. I'm going to scroll just for a second just to show you where the list is. I was supposed to be on another page, but it got covered up somehow. Right there, page 172. See these ones with hearts? Those are the 4 you need to know for the AP test. Okay, if you know those, then you don't have to waste time writing out your Taylor Maclaurins. Okay, I call them designer series. We'll get into it next week. Okay, how to use them, but they're all listed there. They're also on some page in your textbook, but your notes are probably easier to get to than your textbook. It's probably buried under your bed somewhere, right? That's where I always tell you to keep it. All right, you will have to return those at some point. All right, let's take a look at this part then. So for each real number x, it can be shown that the infinite series it's up above converges to the value of e to the x. So a definition of a power series officially, okay, is that if x is variable, then an infinite series that's in this form, which a Taylor and Maclaurin are in that form. Just think of the a that's in front of each one of those could be any number, including a fraction. Okay, we call that a power series when we look at it like that. More generally, we can look like this, and look at that. It has the minus c in it, just like good old Taylor did. Okay, and we just call that a power series centered at c. It's not different than what we were doing earlier this week. Good morning, David. So all we're going to do right now is we're going to try to find the value of c where each power series is centered. Okay, so I want to look for a pattern. If it's just an x, right, just like Maclaurin, we're not adding and subtracting anything but 0. We're centered at 0. Okay. If we have any number in here, so let's say it says something like x plus 2. Okay, and whatever. And then the next one's x plus 2 squared, and so on and so on and so on. The c, notice the pattern. it has a minus sign. So to create that minus sign, I would have had to do a minus minus, meaning that the C value would have been -2. So basically, you're going to do your opposite sign thing, just like we do whenever we come in or out of parentheses, right? When we were doing the graphing stuff in Algebra 2, coming in or out of parentheses, we swap our sign, okay? All right, so let's see if that's enough of an explanation. You guys can get the C's on these three things. So what do you guys think? Help me out in the chat. What do you think the C is on A? And literally all we're doing is the C's. There's way too much space there. What do you think the C is on A? Help me out in the chat. All right, I'm seeing a bunch of zeros. Good. Make sure you are participating in the chat. That's part of your grade, okay? All right, and then what is the C in B? What do you guys think? Lorenzo thinks -1. Maria, good. Natalie, good. Brianna, good. Okay, David, we got to swap the sign, okay? So we're coming in or out of parentheses. We're going to swap the sign, all right? All right, so that one's -1. What do you guys think the C is in C? All right. There you go. It is +1. Okay, so that's all we're doing with that. Good morning, Zeta. Is just what is the center? Okay, let's look at the next piece of this. So we're going to talk about the radius and interval of convergence. Okay. So we want to think of a power series as a function that looks like this, which basically looks like one term of a Taylor, right? Or what we're going to eventually call the general term of a Taylor series, where the domain of F is the set of all X for which the power series converges. Determining the domain of a power series is the primary concern of this section. So it's all we're really going to do is kind of look at the domain and where the radius and the interval are. Note a power series converges at the center C because when we put all of the terms in, it's going to end up equaling the first term, right? It will always equal whatever that first term is. So even if the whole series overall diverges, it will converge at that one center point, okay? So sometimes we have just convergence at that one point, but it reads as divergence when we put it into our series tests, okay? All right, so the series, so there's 3 different ways the power series can converge, okay? So it converges only at C, just at the point, okay? And there's a picture of that right here, right? That's number 1. It converges in an interval, so that's the picture for number 2. There exists a real number, r, greater than 0, so the series converges absolutely when the absolute value, notice that's this little chunk that's in here, right? It's this little chunk here, is less than r and diverges when it's greater than r, okay? So if I want to force something to converge, I need it to be less than the radius. And then the series converges the series converges absolutely, I swear they should say absolutely, right? For all X. That basically means that we have, that it converges absolutely immediately. We don't have to worry about an interval. We know that we have it converging everywhere, okay? All right, I'm gonna give you a second too. I gotta look. Sorry. They're working on a birthday card, I think, for my, for my father-in-law, whose birthday was yesterday at daycare. So we have to make sure that they have the right, it's Papa, not Grandpa. All right, so the number r is called the radius of convergence of the power series. So basically r is standing for the radius. If the series converges only at C, so when we're only at C, the radius is equal to 0. So I would annotate this if we're in that situation that we're only 0, okay? If the series converges for all, the radius is r equals infinity. So this is r equals infinity. The set of all values of X for which the power series converges is the interval of convergence of the power series. Okay. Give me a second. There's also a recorder lesson going. I do not enjoy Friday's recorder lesson. I will not miss that when we go back to work. Okay, so find the radius of convergence for each power series. So we're going to go ahead and we're going to find our radius for each one of these. We are going to revisit our friend, the ratio test. So we weren't done with those tests. They're still part of this. We just had to make sure we learned them before we did this, because we're basically going to apply the ratio test every time we look for interval of convergence or radius of convergence. Correct, Lorenzo. That's another way to put it. Okay. It does tell us the extent to which it converges. So it either converges at a point, it converges on an interval, or it converges everywhere, right? Those are the three ways it could do it. And then, like I said, we're going to see an example of each one of those things happening here in example 2. So you can kind of see what that looks like and how the problem works. Okay. All right, so I copied and pasted, hopefully you have your orange sheet handy. I copied and pasted the ratio test right into here, okay? So we're going to do, I'm gonna go off of that. So when I am doing the ratio test, remember we start the limit as n approaches infinity. I have to put my new series up in the numerator. What do I have to plug into it to get my new series up in the numerator? Can you guys tell me in the chat? All right, I'm seeing a few. I want to make sure we're all there. Or do I only have 4 people paying attention? Now I've got 5. Sorry, I'm making sure we're getting everybody here. Okay, n plus 1, there we go. Thank you. Lester even answered, he fixed it. You did ×1. Thank you for fixing it, Lester. All right, so we're going to put in n plus 1. So I'm putting in n plus 1 factorial x to the n plus 1. All right. Then I've got n factorial, so the original on the bottom, over n. All right. The next thing that I'm going to do is I am going to, whatchamacallit, or I'm going to try to expand it. I'm sorry, I'm a little distracted. I'm trying to make sure that we're getting everybody in class. All right. B, we're going to expand the, the factorial. So it'd be n plus 1. And then the next one, remember, we keep subtracting 1, so it'd be n factorial. And then remember this piece here, I can break that into x to the n times x to the first. And then I'm going to just leave n factorial and x to the n. And now we get to do our favorite part, right? Which is what means we get to cross some stuff out. It's like our favorite thing to do in math class. Although, wait, I have one other favorite thing that's more favorite. Do you guys know what my more favorite thing to do is in math class than cross stuff out? Let's see how well you know Mrs. Ballard. What's my more favorite thing to do? Trig? Maybe, but I think I have something that's more favorite than that. Not Kahoot, no. Not Disney, no. It has to do with, definitely not English. You all know I can't spell. But I'd rather do English than history, I'll tell you that. All right. It's eat pie, people. You've been with me for 3 years. How do you not know that? Eat pie. All right. So we haven't done a Ballard style Kahoot in a while, have we? We should pull one of those out of the whatchamacallit? I don't know, out of the boxes or whatever, the old Kahoots. See, Zeta, you should have answered. You just made it to make sure I knew it. Sure. The Ballard style Kahoots, we did some of them last year. Remember when we used to do them? Or I don't know if you guys weren't in the section with Cameron. We would do them when Cameron wasn't there, and then we'd play again when Cameron came back. So that we would all beat Cameron. He didn't like that very much. Okay, so we're going to keep going on this problem. So we've got the limit as n approaches infinity. And let's see, we're down to now absolute value of n plus 1 times x. And remember when we're plugging into these things, okay, we only have n to plug into. So I can't plug in for that x, which seems a little bit weird, okay, but that's what we're doing. So when I plug in, I would get infinity times x, which is just infinity, which if I look over here at my ratio test, when I'm equal to infinity, I diverges, right? So diverges by ratio test. But when it diverges, we know that it at least converges at one point. So the length of my radius, if I go back up here and I look at what the information that we had, the length of my radius has to be equal to 0. So this is an example of a 0 radius. So your radius is equal to 0. All right, let's look at B, okay? So again, what are we going to plug in for our ratio test, okay? We've got the limit as n approaches infinity of what goes in my numerator. What do I have to plug in? Help me out in the chat. I want to make sure we're paying attention. Okay. N plus 1. So I'm going to do 3x minus 2 to the n plus 1. And then all over the original, which is 3x minus 2 to the n. All right, for sure right here, before I even split anything up and make it so I can cross stuff out, I can get rid of those 3's, couldn't I? So now I'm going to split this up a little bit. So n approaches infinity. I'm going to split this into 2, right? It's the same thing as saying x minus 2 to the n times x minus 2 to the first over x minus 2 to the n. All right. We are going to cross some stuff out again. We get to cross out the x minus 2 to the n's. And look at what we're left with. The limit as n approaches infinity of x minus 2. And that's really it, right? Because I can't plug, there's nowhere for me to plug infinity in because n is where the infinity goes. So the limit is actually equal to the absolute value of x minus 2. In order to force that limit or that function to converge, we want it to be less than 1 to converge absolutely. Okay. So this is this is the radius. Okay. And this, we're going to use less than 1 so it converges absolutely. Converges absolutely. Okay, so we're forcing absolute convergence because of the way it was set up. Making sure we all have a chance to write it. Okay, you ready? Here comes the next one. So, finding the radius of convergence again. Again, what do I need to plug in? I haven't asked a whole lot of questions today. We've been kind of repetitive. We could copy and paste that in for like the 3rd time now, right? But at least I know you're still paying attention. There we go. Okay, we're going to put in n plus 1. Perfect. So we've got the limit. We're using the ratio test as n approaches infinity. Absolute value of, this time I'm going to have, actually I'm going to do the flip and multiply on my double fraction because I've got a fraction to begin with. I get to ignore the -1 because we're in absolute values. Okay, so then we have x to the 2 times n plus 1 over 2 times n plus 1 factorial. And then we're going to flip the original. So 2n plus 1 factorial over x to the 2n plus 1. Okay. I'm going to keep going. Limit as n approaches infinity. I'm going to distribute in this 2 and add the 1 all in one step. Okay, so I'm going to do two things at once. We've got x to the 2n, and then 2 times 1 is 2 plus 1 would be 3. And look at that. It's going to be the same in the denominator because it's the same exact calculation. We're just going to throw a factorial after it. And then we still have this. Plus 1 in the exponent. Okay, I wrote smaller than I did yesterday, but still too big, I think. I might have to move it off to the side. I'll see if I can squeeze it in. All right, so you've got the limit. I'm going to do some rearrangement and taking this apart so I can do some canceling. So I can break this into x to the 2n times x to the third. Okay. And then let's see. I'm going to bring this guy up front and break him into x to the 2n times x to the first. I'm going to leave this alone, 2n plus 1 factorial. And then I'm going to expand this guy. So let me do that one in a completely different color. So I'm expanding this. So we'd get 2n plus 3. I subtract 1. I would get 2n plus 2. I would subtract 1 again. I get 2n plus 1 factorial. All right, what's the next step, everybody? What do I get to do? What do we get to do? Natalie seems to be yelling at me today. Or are we just excited that we get to cancel? All right, we are in fact going to do some canceling. It's okay. Natalie, David's defending you that you're just excited. Okay, here we go. We're going to cross some stuff out. So the 2n's are gone. These are gone. And then look at this. I could subtract my exponents, couldn't I? Because this is the same base, and so I could subtract those exponents. So I would say I've got the limit as n approaches infinity. X to the third minus 1 would be x squared. And then over here, I still have this junk left in the denominator. So 2n plus 3 times 2n plus 2. All right, I'm ready to substitute in. Okay. And remember, when I substitute in, I only get to put it in for the n, not for the x, because that's my limit is for n. All right, so we have x squared times 1 over infinity times infinity. So we know that this part here is going to be 0, isn't it? So x squared times 0, which is going to be 0, which is less than 1 in our ratio test. So therefore it converges absolutely by ratio test. I'm going to give you a minute to catch up, then we're going to talk about the radius. All right. What's the radius on this one? If I converge absolutely right off the bat, what do we get for the radius? Go back up and look at the chart. What did we write down? I don't think you have to. Not on the AP test. I'm in that habit right now because we just came out of the series one. It doesn't hurt. Okay. All right, I got one person who's looked it up. I've got 2 people who have tried. I've got 1 person who has it right. All right. Good job. It looks like, so this is where the radius equals infinity. Because if I came back up here and I read this chart, It says, if it converges absolutely, my radius is equal to infinity. Okay? All right. Who's tired of taking notes? Lorenzo, would you rather stop and read? Yes. But you're the only one that seems to be tired of taking notes. Nobody else jumped on that. We should keep going then, I guess. Or nobody else is paying attention. Natalie's just here. Because it tells us how far, or it gives us some idea of how far it's going to converge. Basically, how far is the series out going to converge? And eventually we're going to turn this into an interval, okay? So everybody wants to keep going. Nobody wants to stop, except Lorenzo. Anna says she thinks she's good. Luis wants to take a break. Okay, there's a few people who have woken up and understood that maybe we don't have to keep going this. For the weekend. No, not for the weekend. You need to do some homework. If you don't have your homework turned in yet, then you need to do some homework. However, it's been a while, and we were talking about Kahoot earlier, so I thought maybe we should play some Kahoot. Okay? If you have a list of derivatives somewhere, you might want to get that out. So go to Kahoot.it somehow, some way. Phones, split the screen duel. I know, Luis, you were on your phone. I'm sorry. But get your Kahoot going, Kahoot.it. I'm going to get Kahoot going on the other machine here. All right. And there is a little bit more of an assignment I want you to do. So as I'm getting Kahoot up, I'm going to try to explain it at the same time. Okay. What I have done is we are heading into that time of the year. We still have some material to cover, but we're starting to need to get to that review time of the year. And there's material that's old that you guys need to review, okay? So instead of finishing this lesson and assigning homework on this one, we're not quite